Okay. Make sure that you are very consistent with waves. Okay. Do not skip or do not let things pile up. It's a big chapter. This is like 88 pages on this because this isn't a single chapter. It's like three chapters combined. First you've got general waves, then you've got sound waves, then you've got, what else? Then you've got superposition, then you've got stationary waves, right? So these are like 3 to 4 chapters combined into one. So that's why think of these as like three separate chapters, but I teach it in just one go, so that you do not miss out on anything. Okay, so let's start. Once again. Okay, yes, Kaima, how you doing?
I'm good,
Yes, Kaima.
Alhamdulillah.
Okay, sounds good. Yes, Kaima, we are starting waves. Okay, so be ready. Make sure to pay very, very close attention in waves. This is a tough chapter. It requires some complex, connecting the dots. So make sure you are consistent. Do not let things pile up. Okay. Okay. And you can stop me whenever you feel like there's a problem. Okay. So waves, we're starting waves and it's a long chapter. It's going to take some time. So we'll go over it slowly. Now, what is a wave basically? I'm sure you've seen like ripples in water, right? What happens is that, for example, if you've got a water droplet, dropping over here, that you will see that ripples forms, right? These ripples are basically what we call water waves. Now, if you look at the wave closely, there was a water droplet over here, but somehow that disturbed the water across the entire portion of that puddle, right? It is disturbing everything. And what's happening is that this water particle did not even move by itself, but somehow energy was propagated away from this point, right? That's what wave is. That a wave is essentially that energy moves away without the water itself moving. It's not as if the water is literally flowing there. The water is staying there, but somehow energy is flowing from, through the medium. Okay. It's kind of like the water is providing a surface, and on that surface, energy is moving away, right? That's basically what a wave is. Essentially, most of the stuff that do is has wave motion associated. For example, the sound of a drum reaching your ears, that's a reaching. Or for example, the fact that you can listen to me right now is due to waves. First of all, sound is a wave as well. And how can you listen to me? That's also through waves, a special kind of wave, electromagnetic waves, right? For example, how can you see what I'm writing? That's light. That's also an electromagnetic wave. How can you, how is internet being transmitted to you? That's also a property of light. Then, what else? You have heat. Heat in form of infrared is also, an electromagnetic wave. You can think of heat as infrared waves, traveling across you. Then, what about Wi-Fi? The single most important thing in our lives, Wi-Fi. That is also an electromagnetic wave. Wi-Fi is, in fact, and Wi-Fi and Bluetooth are actually electromagnetic waves, microwaves and radio, right? That's how you can use microwaves and radio to transmit Wi-Fi, right? Although they're not the same microwaves in your microwave oven, but they are of a similar frequency, right? So everything that we do has with electromagnetic waves, right? Waves is a very important, you could say, a core foundation or building block of physics. And any kind of rotation, any kind of rotation slash any kind of vibration is also what we call a wave-like motion, right? There is, in fact, a special chapter dedicated to this rotation and vibrations, which we call simple harmonic motion. Simple harmonic motion. And this is a big chapter which we study in A2. This is about the motion of all repeating, repetitive motion. For example, anything that reoccurs after a certain period of time. It could be, for example, an oscillating pendulum. It could be, for example, an oscillating swing. Or, for example, it could also be anything that's vibrating. Or, for example, it could also be a fan that is completing, circles and circles. That's all rotation slash vibration, that it is completing a certain motion in a certain amount of time and it is repeating, right? So that also counts as waves. But we study that specifically in simple harmonic motion in A2. I'll give you a little bit of flavor of simple harmonic motion because it is important to understand that to actually, picture what waves are. Okay. Now, what is a wave essentially? A wave is, these are like the battle ropes that you've probably seen in the gym or somewhere, that this person is going to take this rope which is connected to the wall and is going to swing this rope up and down, right? Now, the rope is staying there. All the particles of the rope are, as it is and in the motion. But he is basically swinging the rope up and down. And that up and down is translating energy to the end of the wall, right? Somehow that up and down vibration is traveling along the wave, right? That's essentially what a wave is. That the rope itself is not moving, but somehow energy is moving away from the rope without the rope moving itself. That's what a wave is, right? And by the way, these are all just applications of what I just said earlier. I would recommend that you read it out. Now, for example, let me show you what a wave looks like. Top view and side view. Check these out. For example, now of course this is droplets of water forming puddles. Right now, this is the top view. Like if, for example, if you view the puddle from the top, then this is exactly what you'll see, right? And there are a few things that I can change to change the pattern of it. If I increase the frequency, you'll notice that now there are more drops per second. And I could also increase the amplitude, which is kind of like how hard the water is hitting, how big of a drop is it making. Now, this is the top view. Now, let me show you the side view. Check it out. If you look at the side view, this is essentially what a wave is, right? It's not as if the water itself is moving to the right. What's happening is that water molecules are kind of like passing the energy on to other molecules, and the water molecules themselves are not moving. That's essentially what a wave is, right? So this is what it looks like. So now, if you were to look at the top view, by the way, this top view, these are what we call wave fronts. I'm sure you've seen this pattern. This is what we call a circular wave front. Now you might think, how the hell is this a wave? Circular wave front. This is essentially propagation in all directions. Propagation basically just means it is the travel of something, or it is something that is moving. Propagation or originating. Propagation of waves in all directions. Right? What does that mean? That means that waves are traveling in all the directions, right? From here, then from here, and then it's like millions and millions of waves traveling in all the direction, millions and millions of waves traveling in all the direction, right? So this is what a wave front is. You could picture 3D waves traveling in all direction, right? It's just like millions of waves coupled on top of each other. Now, by the way, one important information. This line, the distance between this line actually represents one wavelength, right? Just telling you this beforehand. We'll learn more about wavelengths later on, but this distance between two wavefronts is what we call one wavelength. And by the way, generally, this also represents that, for example, where do you get a crest? So that means if one crest pops up over here, the second crest would pop here. Okay, I haven't drawn it accurate, but that's what it means. Okay, so you could imagine that one wave is completed through this distance. Okay, you'll learn more about that soon. So this is what the circular wavefront looks like if you're ever confused about it. Okay, now, how do we write down the definition for waves? Waves is essentially the transfer of energy and momentum, right, without a transfer of the medium itself, right? This is a very important definition. Transfer of energy and momentum without the transfer of the medium itself. That's it, right? So this person is using energy from his hand to somehow oscillate this pendulum up and up and down, and energy is propagating away from the source without the rope moving itself. The rope over here is still in my hand, but somehow this point of the rope is transferring energy into all of the consecutive particles. And now, we have two type of, propagation types, by the way. Again, propagation means it is travel, right? That's just an easy word for it. Now, you've got two types of, travel types of, wait, there are, however, two types of propagation types. Yep. Right now, you've got a transverse wave and you've got a longitudinal wave. Now, what is a transverse and longitudinal wave? In transverse wave, particles actually oscillate perpendicular perpendicular to the wave motion. What does that mean? That means, for example, if the wave is going forward, the particles or the rope or whatever that's oscillating is actually going to oscillate perpendicular to the wave motion. So that means if the wave is going right, the particle is going to oscillate up and down. It's going to move up and down. But for example, if the wave is going in this direction, then the particle is still going to oscillate up and down relative to that wave motion. So it always forms a 90-degree angle. So this is the wave motion, right? It always oscillates up and down. You can think of it like this, for example, this is the oscillation and the particle would be going forward, right? Exactly like, for example, the vibration of a rope, right? The wave motion is going to the right, but the particles themselves on the rope are oscillating up and down. The wave is moving right, but the particles are oscillating up and down. So that's what a transfer phase is. Okay, make sure you remember the definition because that's very, very frequently asked. Now, what would be a longitudinal wave? In those, particles oscillate parallel to wave motion, right? That means that if the wave is going forward, the particles are actually going to oscillate back and forth, right? Kind of like this, right? I can see it, but you can think of it as, in fact, draw a ball. Okay, right? You can think of it going like this. It's going back and forth, right? And this back and forth is basically transferring energy along the wave. You can think of like a slinky, right? A slinky is essentially forming a longitudinal wave because, for example, you push it along this side. What happens is that the entire wave travels along this portion and forms, it forms a longitudinal wave where the particles are oscillating back and forth. Example is a sound wave. One of the most important longitudinal waves is a sound wave. Sound wave is a longitudinal wave. And this is how you kind of picture a longitudinal wave, right? This is, you could think of these are where the particles are concentrated, and this is where they've got a little bit of breathing space. Then particles are concentrated, and then they've got a little bit of space. And this, where the particles are concentrated, that is what we call a compression. And when the particles are separated, that's what we call a rarefaction. Let me show it to you how the motion looks like. Waves is always understood with visualizations. Let me show you a sound wave. Oh, check this one out as well. This is what a transverse wave is. One second.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
Yep, and one more. Where's the sound wave? Oh, that was it. Ah, here it is. This is what a sound wave kind of looks like. It's pretty weird, but that's what it looks like. It's difficult to visualize a longitudinal wave. Whoa. That's what it looks like, right? You can notice that the particles themselves are not going forward, right? It is the particles themselves are not moving forward. Keep that in mind. They're transferring energy to the right without moving themselves, right? They push to the right and they come back to their original position, right? That's what longitudinal waves are. You'll see more of those soon. What is this? One second. Yep, it's the same thing, right? So for example, uh, one second, fixed. Check it out. So if I were to make a transverse wave, this is what it look like, right? Then, if for example, oh, it won't stop. Okay. Now, if I were to move it left and right, then this is what it look like, right? I am transferring energy to the right by the particles oscillating back and forth, right? That's what it looks like. Okay. One more thing. Very important to visualize longitudinal and okay. Now this is trying to visualize a longitudinal wave using a transverse wave, like the comparison between both of them. Okay. Check it out. Think of it like this. Try to analyze the motion of the longitudinal wave. The part, if you like, notice one line, right? Like let's just try to focus on one line. That one line itself just moves back and forth, but they move back and forth in such a way that they make sure that the wave travels along to the right. They collectively push all the particles to the right, and then they collectively come back down to their original position, and that continues, till you keep running the wave. Okay, so that's what a longitudinal wave looks like. Now, how do we graph waves? Okay, this is an important one. Now, I'm going to use an example of a pendulum to help you visualize how we draw waves graphically, okay, on, a y and x axis. So if this is a pendulum, of course, what will happen is, it's going to oscillate back and forth, right? That's just like a swing. So it's going to go in this direction and it's going to go in this direction, right? So let's call this as x is equals to 0 displacement. At this point, there is no displacement, okay? Now, if, for example, if it moves to the right, what's happening? You have x is equals to positive displacement, right? And then what's going to happen? It goes to the right and then it comes back down, right? Back to 0 displacement. Then, so you go here, let me draw it like this. So you get positive displacement, positive x, and then you come back down. Then you get negative displacement because you're switching directions, and then you come back down to 0. That's what we call as one whole oscillation, right? So one whole oscillation would be you go away, you come back, right? And then you go the other direction and then you come back to your original position. That's what we call as one whole oscillation or one complete swing. Okay. Now, what if I were to try to graph that on a graph on, y and x axis? So for example, if I were to plot this displacement with respect to time, okay. Now at the start, my displacement is 0. Okay. My displacement is 0. Then notice what happens when I go on the other end. That's, x is equals to, or, let's call it positive x. Okay. Then I have some amount of positive displacement x after certain time, time in seconds. Then what happens is, then you come back to your original position. Doesn't that mean after some time the graph has moved forward and you're now back to your original position? And notice how we draw the graph. You go up, and then what happens? You go back down, right? That isn't clean at all. Oh, let's see if we can mirror it. Oh, oh, great. Okay, right? So this is what it looks like, right? Because you went back up to maximum displacement and then you came back down. Now notice what's going to happen after this. You get negative displacement after this because you've switched direction, right? Because you consider the center to be 0. So this is negative x. That means if you assume that this is the same distance and this is the same distance, then you go exactly the same distance below. Let me see. Check this out. Right? Now, after some time, I reach the other end, but now it's actually having a negative displacement x. Right? Then what happens? You go back up to your original position, right? At this point, you're over here. Then you go back to 0. So that means after some certain time, you go back to your original position. And that's what a wave looks like, right? You see that it forms a wave, right? And if I were to duplicate this, that is essentially what the wave motion looks like. That's what a wave looks like. You can plot a wave by using a pendulum, because that pendulum essentially follows this wave-like pattern. The displacement time graph of it is essentially what a wave looks like, right? Let me see if I have the 1 second. There was another one for pendulums. Let's see if we have a graph for that. There should be. What is it? Pendulum lab. Energy graph. Okay, we do not have the graph for displacement. But you can think of it like this. Let me show it to you. Check it out. There's a different, it's an oscillating pendulum, and you will see that how the displacement is varying. This is how the velocity is varying, by the way. This is how the velocity is varying, right? But this is of less use to us because it's not showing us the displacement graph. But if you were to plot a displacement time graph, then it would look exactly like this. Okay, but this is with respect to time. You've got to be very careful of the axis. That is, if I were to plot the displacement with respect to time, I were to use a stopwatch. But sometimes you get a different axis where it's displacement with respect to distance. This is the distance covered by the ball. Now, why would this go forward? Why would this keep on increasing? Because distance is a scalar quantity. It is always going to keep on increasing, right? Just like time in this case, because the displacement, comes back and forth, right? It goes to positive x, it comes back to zero, then it comes to negative x, and then comes back to zero. In this case, what would happen to the distance? The distance would keep on increasing, right? Distance increases, increases. So the distance is going to keep on increasing. So this information is very important because the graph for a displacement distance curve gives you different kind of information, and a displacement time graph gives you a different kind of information. So they're both very different ideas, and they will give you different pieces of information. So they're both very, very important, and you have to make sure you do not confuse them. Okay, now let's learn a few terminologies. What is displacement? First of all, displacement is basically just the distance from the mean position. From mean position, that's it. Right? So that means, for example, I am saying that my displacement is, let's say, 3 meters. That means that I am actually plus 3 meters away from my mean position, because this would be my mean position, by the way. The center point where displacement is zero is what we call the mean position, right? If, for example, my displacement is -3, then that would probably mean this point somewhere over here, right? So that means my displacement is -3 over this point. So that means I am 3 meters on the left, depending on what you call -3 and +3. Okay. So that's what displacement is. Pretty easy. Then what is amplitude? Amplitude is a specific form of displacement. It is the maximum displacement. You have to learn these definitions. They, ask these pretty often. It is the maximum displacement from mean position, right? So that is the highest point you go from mean position. So that would mean this point. This point is your amplitude. This point is your amplitude. By the way, the bottom point is also the amplitude. Okay, it doesn't matter, right? But it is a scalar quantity, by the way, right? So for example, amplitude is a scalar quantity. So that means your amplitude could either be plus or minus, right? But we don't really care about the plus and minus, because that is just going to make it clear that is it on the left side or is it on the right side. For example, on the pendulum, right? For example, the displacement over here is 5 centimeters and the displacement over here is -5 centimeters. The amplitude, the highest displacement is -5, or 5, but the minus and plus sign is just telling me where is it. That's it, right? So the magnitude is more important. The magnitude is More important. Okay. Now, what is the wavelength? Now, keep in mind, you can only find out the wavelength if you have a displacement with respect to distance curve. You have to make sure that your axis is telling distance, not time, because this is what we measure as one wavelength. This is what we measure as one wavelength, or this is what we measure as one wavelength, right? Wavelength is a unit of distance. So that means you have to see what is on your x-axis. It is distance, right? If it is distance, that means that this distance will also give you, something that would have the same units as distance. If, for example, this would be time, then this distance would not give you a wavelength, because that's a unit of time, right? Then this time would actually be something else, which would not be one wavelength. You can't call it a wavelength because the units would be different, which you're measuring it from, right? So how do we define one wavelength? The easy way is, it is the length of one wave. That's pretty dumb. This is the length of one wave. Everyone knows this, right? But that's not exactly the right answer. It varies. You could also say it is the length between two consecutive crests. Consecutive crests. Okay. Or it is the length between two consecutive troughs. Right. Now, what is a trough and a crest? The crest is the peak. This is the crest. And this is the peak. Sorry, this is the bottom, or this is the trough. The lowest point is the trough. Right. So trough to trough is one wavelength. Crest to crest is also one wavelength. They have to be consecutive. Now, this was the definition up to IGCSEs, right? That this is one wavelength, this is one wavelength. This is also one wavelength, by the way, right? This distance, right? In fact, they would be exactly the same. This wavelength, and this wavelength, they're exactly the same. But it is not necessary that these are the only points. Because, for example, if I were to take this line, right, and if I were to move this along, let me make it a bit larger. Now, this ruler that I'm using, it is essentially what one wavelength is, right? Because I literally just, copied it from over here. It could be possible that there are multiple other points which would also mean one wavelength. For example, if I were to move the ruler like this, then, one second. Okay. Then these 2 points are also one wavelength. I could move the ruler along further. These 2 points are also one wavelength. These 2 points, now you're at the crest. This is why do we call it crest to crest? Because it's easy to spot. But these 2 points could very well tell me the wavelength as well, right? There's a condition for that. I'll tell you the condition soon. For example, uh, these 2 points, they could absolutely tell me the wavelength as well, right? This point and this point, because they're exactly separated by one wave. Okay, I'll tell you how to spot these soon. But the point I'm trying to make is that there can be multiple points that you can take, which would also be one wavelength. That is going to be very helpful when you solve questions where the graph is pretty complicated and you can't really figure out what is the distance between crest to crest or trough to trough. Okay, so now the A level definition would be, it is the distance between two particles in phase. Now, this is a very dangerous and scary word for you guys. I know it was for me as well. I lost it because of this word when I was in my A levels as well. I absolutely hated it. It was the single thing that I hated the most as well, because it was not taught well. But don't worry, that's not what's going to happen with you, because you're learning from me. Now, we have, in phase, we have like a lot of time dedicated to this. But for now, I'll just tell you that phase is essentially where the particle is, where the particle slash wave is in its motion. That's it. In its motion. It's kind of like the location of a particle. That's it. Right? Like where along, how far along is it in the wave? That's what phase is. Okay. Now, how do we know what is in phase? Right? Don't worry. We have like a lot of stuff remaining for phase. This is just like the overview of it. Okay. Now, How do we know two particles are in phase? Two particles on a wave are in phase if they have two things. They have the same displacement from the mean position and they have the same instantaneous motion. What does that mean? That means I'll make it, okay. So for example, let's choose this point. And so this would have a certain displacement from mean position, right? There would have to be exactly another particle along the wave, which would have exactly that same sort of motion and it would have the same sort of displacement. So if I were to extend this graph on the other end, this particle has exactly the same displacement, right? So for example, if this is +3, this particle has +3 displacement and so does this, which means they have, they tick this, they tick this condition that they have the same displacement from the mean position and they have the same instantaneous motion. Now, this basically just means that for the swinging pendulum, you can try to visualize it, I'll show you. For the swinging pendulum, let's call this A and let's call this B. A and B are exactly the same in its motion. Now let me elaborate and show you the pendulum of what I'm trying to say. For example, if I were to draw the pendulum, okay, and so this is like +3, okay. So I know that if I were to draw this pendulum, right? So this is not the complete oscillation. So let's say this is the highest point. Okay. Now, this is the point of, by the way, it's also going to go on the other side. Okay. Okay. Right. So this is the other side. Now, this would, this displacement would absolutely be the amplitude, and so would this, right? Now, what did I mean by position A? So for example, I showed you how to plot a wave using the pendulum, right? So for example, if I'm talking about this point A, then of course this would be somewhere over here, right? It has not reached the amplitude yet. So let's say that this amplitude, this displacement is +3. Okay. So that means I'm talking about point A. This is point A, right? Then what happens? Then you go to the highest point. So that means on the graph that you're on, this point. Then you come back to x is equals to 0, right? So you're back over here. Now, then what happens? Then you go to the negative side. So now you're over here on this wave. Then you go back to the 0 mean position and you're back to this point. Now, notice what happens over here and over here. Do you notice that the oscillation has restarted now? So that means that in this motion, you are back at A. So essentially, these 2 points, A and B, are the same thing. They are in phase because they have the same displacement from mean position and they have the same instantaneous motion. That means if you were to take a picture of the swinging pendulum, A and B would look exactly the same. They are in the same position along their motion. That's what we mean by that they are in phase. So A and B are in phase since, right? Since they have the phase difference part, we have, like a whole dedicated lecture on that. Since they are, but for now, just for the sake of argument, you can say that A and B are in phase by just these two conditions, that they have the same displacement from the mean position and they are in the same instantaneous motion. Okay. Since they are in the same instantaneous motion with same displacement. A, and this is also equal to B. Okay. So this is like separated by a time gap or like a distance gap. Okay. Separate, in fact, I'll write that answer. Separated with a time gap, with a time interval. Okay. For now, if you understand this about phase difference, that's it. That's all you need to know, right? The details will come later. Don't worry. I'll even teach you some stuff about sine theta. I'll teach you some stuff about cos theta, the unit circle, the phase, right? How does like a phase even come by? How do you even get sine theta and cos theta values? That's very important. And you will see that we will try to relate. We will try to relate the unit circle, right? The unit circle with wave motion. And that is going to be absolutely beautiful of, how we somehow relate wave motion with circular motion, right? This circular motion of this, this arrow can also be translated into wave motion. And how that is very interesting. Okay, so we've got a lot of time dedicated on that. Okay, one more definition and then we'll stop the class. So, what is time period? Now, time period is a very important phenomena. That is just the time taken for one complete oscillation. That's it. That's what time period is, right? So that means, for example, that it is the time taken to go from highest point back to mean position, then on the left side back to mean position. This would count as one time period, right? So for example, if I were to draw a graph of it as well, and by the way, you can only measure time period if if the x-axis reads time, right? Because that's only when you can measure time, because this is with respect to time. This has to be displacement. This is always displacement, right? Let me plot a few waves. Okay, right now on this graph, this time period from here to here is what we call one time period, right? It is the time taken to complete one oscillation. That is what one time period is. Or it could also be this. This is equally one time period as well, right? Because the time from crest to crest is also going to be equivalent to one time period. It is going to be the same rule as wavelength. The the distance from crest to crest and trough to trough is also going to be one time period, right? So the time taken to complete one oscillation, that is always going to be one oscillation. Oh, by the way, another thing. So if this is one oscillation, then you can also make quarters of oscillation. So that would mean that if you go towards this side, this would this would be as 1/4 time period. It's a quarter of an oscillation. Then you go from here to here. That's another quarter of the oscillation. Then you're back to this point, right? So you've completed half a wave at this point, or half a time period, right? Then you go to this point. Then that's another quarter of the oscillation, right? Then by the time you get to this point, you've completed the last quarter of the oscillation, right? So when you add up all of these, 1/40 plus 1/40 plus 1/40 plus 1/40, they all add up to one time period, right? So that is what one time period is, okay? We'll do the difference between frequency in the next class, but that will be all for today. Okay, sounds good.